parallel with your resistance, which you are using in the device modeling problems, okay? And the condition is, you have to make sure that we're going to do some examples on source transformation. In last semester's final, we had like so we want you to know this theorem. Normally, that's like an alternative thing where you can go from one to the other when you're solving the problems. But we want you to know that theorem. So I think we asked a question only on source transformation theorem in the final exam last semester. So we're going to do examples on that, okay? So once we thought about that, then we started to actually identify this one as a Thevenin, the one on the left, and the one on the right, the current source in parallel with a resistor, as the Norton equivalent circuit. And we ask ourselves, how do we get those equivalent circuits given a random circuit? And we looked into the situation as first, like with resistors and independent sources. We talk about two things. We talk about finding the Thevenin voltage. We talk about finding the Thevenin resistance. And along the way, we made a definition for VOC and ISC. What was VOC? What was VOC? This is the open circuit voltage. So given any random two terminals, right, leaving them as it is, not connecting anything, if you define the voltage from A to B, that's your VOC. What is the ISC? Short circuit current. How do you find that? You're given a pair of terminals. You short them. Label the current through them. Can you pick the polarity randomly? No, right? That's what we discussed last time. The polarity is not random. If you want this equation to hold, you have to be careful when you say, because we define the VOC and then we say VOC is equal to VTH, right? And then we find ISC, then we say VOC equal ISC times RTH. Now, all those equations are correct for a particular polarity choice, okay? You have to be careful how you define VOC and how you define VTH in that equivalent circuit so that VTH becomes equal to VOC, okay? Any questions about that? That's generally one of the parts that we have lots of errors. So if you have any questions, we can go through this again. Okay, very good. So we started looking into a couple of examples. We did 2 examples, right? And so we said this is how we find VTH, right? We find the open circuit voltage, and then we say VOC is equal to VTH if the polarities agree. In order to find RTH, you can find the short circuit current and use this equation to get RTH. Or, in order to find RTH directly from the circuit, what do I do?
Kill the independent source.
You kill the independent sources. Killing the independent source is not necessarily removing it, right? Killing it means setting its value equal to 0. Setting the value equal to 0 for a voltage source means shorting it, 0 voltage. And setting a current source equal to 0 means that making an open circuit, 0 current, okay? Once we get rid of the independent sources in the circuit, then you can find the equivalent resistance seen from those 2 terminals of interest. Now, if you have only sources, independent sources, when you kill them, you're not going to have any sources, so you will be left with resistors only. And in that case, you know how to find an equivalent resistance. Parallel series combination, delta to y, y to delta, whatever you want to use. But if you have a dependent source left in the circuit, then we didn't exactly know what is the equivalent resistance of a dependent source. That's what we started discussing last time. And this brought us to the fact that if you just take any random circuit, okay, now it could be dependent sources, resistors together, and if the question is, this is circuit 1, this is circuit 2, and the circuit 2 is just a single resistor, okay? Don't know exactly what circuit 1 is, Circuit 2 is a single resistor. And let's say this is R equivalent. The question is, what is R equivalent? Okay? And then our definition for equivalent circuits says that whatever you do to this, you do to that, and then you should have the same voltage current characteristics. So then we said, we can just, if I put like a random voltage source in both cases, and if I measure the current to it, so if I use the same values over here, I know that I'm going to get the same currents. But this circuit tells me that V test over I test is equal Req. And because I don't know Req, but I know that this is true, I can go to the original circuit and find a V test over I test and find what Req is. Okay? It's very important to understand why we are doing that. We're going to keep doing that. We're going to do tons of questions, but it's important what we are doing here. Okay? Any questions? Okay. So, I keep pointing here. So this brings us to the test source method. Could be a test voltage or test source. It doesn't matter really what you connect here. Okay? The important thing is to do the same thing. Could be a source, could be a voltage source, could be a current source. But if you